Aerodynamics is the science of how to fly. Jetman, pictured here, represents the fulfillment of a dream that can be traced back to ancient times. It took many centuries to make the discoveries and achieve the technological breakthroughs that allow him to speed through the air with a small pair of carbon fiber wings and 4 microjet engines. In ancient Greek mythology, Daedalus and his son Icarus attempt to escape from the island of Crete using wings made of wax and feathers. Disobeying his father's warnings, Icarus flies too high, where the heat from the sun melts his wings. He falls into the ocean and drowns. In the late 1400s, Leonardo da Vinci became fascinated with flight and sketched a number of mechanical wing devices. Like many others before him and after him, he drew his inspiration from the birds. Unfortunately, his design would never have gotten off the ground. Humans are just too heavy and don't have the muscle power to achieve flight by flapping wings. The first real breakthrough came from the Montgolfier brothers, but their approach was entirely different. The brothers owned a paper manufacturing company. After noticing that a paper bag would rise up into the air when held over a fire, they decided to test this principle using a much larger bag with a fire suspended below it. A sheep, a duck, and a rooster became the first lucky passengers. Fortunately, they landed safely, and a few months later, Étienne Montgolfier made the first manned balloon flight. On December 1, 1783, Professor Jacques Charles and the Robert brothers made a successful flight from Paris in a hydrogen-filled balloon. Hydrogen, being the lightest element, rises just like hot air. To descend, the pilots opened a release valve to let some of the gas escape, then tossed out bags of sand to slow the descent if they were coming down too fast. This method of controlling altitude was cumbersome, and there was still no way to control the direction of flight. Henri Giffard attempted to solve this problem by giving a more streamlined shape to the balloon and mounting a steam engine and propeller in the carriage. This made some rudimentary directional control possible, but only in very light winds. Meanwhile, others were trying to solve the problem of heavier-than-air flight. Otto Lilienthal made a number of flights in gliders from a hill on the outskirts of Berlin. He was able to control his direction of flight by shifting his weight forward and aft, and from side to side. Unfortunately, he was killed after hitting a gust of wind and stalling the glider. The Wright brothers diligently studied the writings of Otto Lilienthal and began building and testing their own gliders. In addition to making extensive observations of birds in flight, they also built a wind tunnel in their bicycle shop to better understand the principles of lift and aerodynamic control. The last piece of the puzzle was to develop a lightweight engine, which their mechanic, Charlie Taylor, was able to build for them. Everything finally came together on December 17, 1903, and the Wright brothers were able to make the first successful powered flight. The amazing short film in the next slide has actual interviews with people who knew and worked with the Wright brothers, including their mechanic, Charlie Taylor.
What the Wrights had achieved at Kitty Hawk barely evoked passing attention in a nation whose people were absorbed with the problems of a dynamic new age. There were other less celestial wonders closer at hand: the automobile, the telephone, the motion picture. But at number 7 Hawthorne Street, December 17, 1903 was a momentous day. The young girl who was then the Wrights' housekeeper, Carrie Grumbach, remembers,
"I remember the telegram when it come, that they had flown, that they had done what they said they would do. They always did as they had planned."
The telegram from Kitty Hawk had a special significance for the mechanic who worked in the Wrights' bicycle shop, Charlie Taylor.
Of course, I was greatly pleased to know it had been accomplished, but at that time it didn't seem to be anything wonderful at that. I started on repairing bicycles back in the 80s. And then I later went to Dayton and built bicycles for the Stoddard Manufacturing Company. And they were just starting up in the bicycle business. Then I got acquainted with the Wrights, and I built bicycles for them. I did all the repair work while they went down to Kitty Hawk to try out their gliders. Well, and all they needed was power to keep on flying. Why, then when we designed the motor, I made all the different parts in the motor. I even made the crankshaft. So I made it out of a solid block of steel, about 32 inches long, 6 inches wide, and 1 5/8 thick. Cut it right out of the solid block by drilling holes and knocking out large pieces out of it, and then turning it up in the lathe. The motor itself, from the time I started till I had it ready for test, was 6 weeks. 50 years ago, I can remember as though it was yesterday almost.
There was not a complete indifference to the Wrights' discovery. A small group of Americans were laboring to further the art. And in Europe, where the airplane's military potential was quickly realized, a fresh wave of enthusiasm for aviation followed the Wrights' success. In France, Blériot, Farman, and Briquet were flying airplanes of their own design. The Englishman Curie and the Brazilian Santos Dumont, most of whose experiments took place in France, also captured the imagination of Europe with successful flights. The Wrights had offered to demonstrate their airplane to the United States Army shortly after their first successful flights. The Army declined, preferring to develop its small fleet of balloons as an air arm. Oddly, it was a young balloonist lieutenant of the Army who finally was instrumental in obtaining a chance for the Wrights and their airplane, Frank P. Long.
After 4 long years of failing to recognize the Wrights, finally, in December of 1907, the Board of Ordnance and Fortification granted an interview to Wilbur. At once, he inspired their confidence. This led to a contract in February of 1908 between the Wright brothers and the Signal Corps, in which they agreed to furnish an airplane that would fly 40 miles an hour, carry 2 persons, remain in the air for 1 hour, and, strange to relate, was to have some kind of a device by which, in case the motor stopped, it could be landed without crashing. In the summer of 1908, Orville Wright brought to Fort Myer, Virginia, the airplane that was to fulfill the specifications of the contract. Day after day, we watched him fly around and around the field in his tuning-up flights. And finally, on the 9th of September, he broke the world record by staying in the air for over 1 hour. On landing, he came to me and said, "Would you like to go up?" You can guess my answer. And I made my first flight in an airplane that day with Orville Wright, 6 minutes and 40 seconds.
Lieutenant Law became the first military officer ever to fly in an airplane. 8 days later, tragedy struck. On a flight at Fort Myer, Lieutenant Thomas Selfridge was killed, Orville Wright injured. Shocked, but not deterred, both the Army and the Wrights moved to improve the airplane.
The Wright brothers made 2 major breakthroughs with their successful flight at Kitty Hawk: aerodynamic control and powered flight. Aerodynamic control was achieved by means of control surfaces connected to cables and pulleys that could be deflected to alter the airflow around the aircraft, thereby altering its orientation along 3 axes: pitch, roll, and yaw. This form of aerodynamic control, referred to as 3-axis control, was much more precise than the weight shift control utilized by Otto Lilienthal in his gliders. The aircraft could be rotated along 3 axes. The elevator, located out in front, could be deflected up or down, causing the pitch to move up or down along the lateral axis. Deflecting the rudder left or right caused the front of the aircraft to yaw left or right around the vertical axis. The right and left wingtips could be deflected in opposite directions, causing the aircraft to roll left or right along the longitudinal axis. After making some improvements, the Wright brothers took their aircraft over to Europe, where they made a number of public flying demonstrations. The following video shows fascinating footage made when a movie camera was placed in an aircraft for the first time. Note the elevator out in front being deflected up and down to control pitch. The Wright brothers made their aircraft roll along the longitudinal axis by deflecting one wingtip up and the opposite wingtip down, or vice versa. This system of wing warping was modeled after their observations of birds in flight. The wingtip deflected upward spoiled the lift on that wing, causing it to drop, while the wingtip deflected downwards on the opposite wing created more camber or curve, which in turn generated more lift, causing it to rise. The Wright brothers' system of wing warping, which they had patented, was soon abandoned by subsequent inventors who favored ailerons. These consisted of panels fitted to the wing's trailing edges that could be moved in opposite directions. Ailerons worked just like wing warping, spoiling lift on one side while increasing camber and generating more lift on the other side. All modern aircraft use ailerons for roll control. The ailerons, elevator and rudder are connected by cables and pulleys or pushrods to a stick or yoke manipulated by the pilot, allowing for full 3-axis control. These control surfaces are called the primary flight controls. In addition, most training aircraft also have secondary flight controls. A manual trim wheel or electric trim button, connected to a small deflecting surface on the elevator, can be adjusted from inside the cockpit to relieve the pilot from putting constant pressure on the stick or yoke. Rudder trim can be achieved by bending a small metal tab on the trailing edge of the rudder, but this should only be done by a licensed mechanic. Flaps are another type of secondary flight control. They consist of a panel on the trailing edge of the wing that can be deflected downwards, simultaneously increasing lift and drag. Deploying the flaps allows the aircraft to make a steeper approach to landing, without increasing airspeed. Large airliners have many other secondary flight controls, such as spoilers, that can be deflected upwards into the airflow over the wing to reduce lift and aid in the descent. Spoilers are also used on gliders, but not on powered training aircraft. Stability is critical for flight control, especially on aircraft that will be used for training. Stability can be positive, neutral, or negative. There are two kinds of stability that are important in aircraft design: static and dynamic. Aircraft designed with positive static stability will return to the previous flight attitude after a pitch-down disturbance. Those with neutral static stability will remain in the new flight attitude, and those with negative static stability will continue further and further away from the previous flight attitude. Dynamic stability refers to an aircraft's tendency to oscillate. Oscillations will dampen out over time in aircraft designed with positive dynamic stability. Oscillations will continue but not worsen in aircraft with neutral dynamic stability, and oscillations will get progressively worse in aircraft with negative dynamic stability. Thus, aircraft with negative static and dynamic stability will be very difficult to control. However, in some types of aircraft, such as high-performance fighter jets, instability may actually be a desirable quality because it makes them more maneuverable. Grumman's X-29 experimental fighter was so unstable that it could only be flown with the assistance of a computer that made continuous movements of the flight control surfaces that were never sensed by the pilot. There are 4 forces acting on an airplane in flight: lift, weight, thrust, and drag. In steady-state flight, all of these forces are equal, regardless of whether the aircraft is in level flight, a climb, or a descent. For example, as an aircraft transitions to a climb, lift will temporarily be greater than weight until the aircraft is established in the climb. Then lift and weight will become equal again. Bernoulli's principle can help us understand the lifting force acting on a wing in flight. Bernoulli was an 18th-century Swiss scientist who discovered that any fluid, including air, exerts less pressure the faster it is moving. Because of a wing's curvature, air moves faster over the upper surface than over the lower surface. The slower-moving air under the wing has a higher pressure, pushing the wing upward toward the lower-pressure air above it. This principle can be demonstrated and accurately measured using a Venturi device, a simple tube that narrows in the middle. As air flows through the venturi, its pressure lowers as it enters the constriction in the middle of the tube, then rises to the previous level as it reaches the larger opening at the other end. As we see in the following video, the same principle is at work even if the upper portion of the venturi is removed, effectively creating a curved surface similar to a wing.
If we can see the air, then perhaps it will help us answer our beginning question: how do airplanes fly? We'll start with a double-winged model in the airflow. The action of the air between the wings will demonstrate a basic principle of aerodynamics. Now, by animation, let's study the airflow in greater detail. First, note that its pattern suggests it is passing through a tube-shaped device. Next, notice that the entrance and exit of the device are the same size. We can measure the openings and find that the ends are each 10 square inches. The middle part is squeezed, creating a throat of 5 square inches. Now, if we direct smoke lines through the device, its pattern will show that something happens to the air where it goes through the narrowed part. What we find is that when the airspeed is 100 miles an hour at the entrance of the device, it is also 100 miles an hour at the exit. Yet at the same time, the speed at the narrow part is considerably higher. It can easily be understood, therefore, that the air increases in speed as it passes through the smaller opening. But the interesting thing is that in order for the air to go at the faster speed through the narrow part, something has to balance this change in velocity, this speed difference. What changes is the air pressure in the narrow part. This pressure is significantly lower than the pressure at either end. But what does this have to do with flying? If we cut the model in half, we would have a profile similar to an aircraft wing section, called an airfoil. You can see how helpful it would be to lower the pressure over a wing. Why? So that the comparatively higher pressure under the wing would push or lift it into the area of lower pressure above the wing. That's part of how an airplane flies.
Another force that helps create lift on a wing comes from Isaac Newton's third law of motion. For every action there is an equal and opposite reaction. As air flows over a wing, some is deflected downward, creating an equal and opposite reaction that pushes the wing upward. You've probably experienced this principle when holding your hand out the window of a moving car. By angling your palm down, the wind hitting it is also deflected downwards, pushing your hand up. The same principle works in any fluid, including water. As seen in the following video, jumping up and down on the aquaskipper pushes the blade or water foil forward and water downward, propelling the rider up so he doesn't sink. Even a board can be an airfoil, just not a very good one because it creates too much drag. The curved surface of a wing promotes smooth airflow and takes full advantage of Bernoulli's principle and Newton's third law of motion. A wing can be symmetrical or cambered. Symmetrical wings are useful when the aircraft will also fly upside down, such as an aerobatic plane or fighter jet. Training aircraft have cambered wings. Even the curved surface of an aircraft's fuselage provides some lift. The X-24B experimental aircraft didn't even have wings. Some of the lessons learned from the flight testing seen in the following video were incorporated into the design of the space shuttle. When airflow over the surface of a wing is disrupted too severely, a stall can result. Lift will be lost and the wing will suddenly drop along with the aircraft it is attached to. As the aircraft moves into a dive, airflow over the surface of the wing is restored, along with the lift. It is very important to avoid inadvertently stalling the aircraft, especially near the ground, when there may not be enough altitude to recover. If an aircraft does stall, the solution is to push the nose down and add power to restore airflow to the wing as soon as possible. A stall occurs when the wing exceeds the critical angle of attack, which is the angle between the chord line and the relative wind. Relative wind is the air flowing over the leading edge of the wing, even though the actual wind may be coming from a different direction. For example, imagine you are in a convertible car and parked at a stoplight. The wind is coming from your left, blowing against the left side of your face. When the light turns green and you begin accelerating, the wind will be blowing directly into the front of your face. This is the relative wind. Wing loading is the total weight of the aircraft with fuel, passengers, and baggage, divided by the total wing area. Naturally, a larger wing can lift more weight. Too much weight on the wings can prevent an aircraft from leaving the ground, or worse, cause it to structurally fail in flight. Even though you might be able to get airborne, when maneuvering in a turn or hitting a gust of wind, the aircraft will experience an increase in wing loading. The weight you feel in level flight is 1 g, the same as when sitting in a chair on the ground. If you make a turn in an aircraft or in a roller coaster on the ground, you will feel pressure as you are pulled against the seat by the force of gravity. Depending on your speed or angle of bank, this force can increase considerably. For example, an aircraft in a 60-degree bank will experience a load factor of 2 Gs, or double the normal force of gravity. When making a turn, a pilot will need to increase the wing's angle of attack to maintain altitude. That's because a portion of the vertical component of lift has been shifted horizontally to make the airplane turn. The increased load factor placed on a wing in a turn also causes it to stall at a higher speed. It's important for pilots to remember that the stalling speed, noted in the airplane flight manual and by the white and green arcs on the airspeed indicator, will increase in a banked turn. It is critical for pilots to keep this in mind when making turns in an approach to landing, since staying above the published stalling speed may still result in a stall, and there may not be enough altitude to recover. Aircraft are designed to stall before they brake. In other words, they will stall before the load factor on the wings becomes so great that structural failure occurs, but only up to certain speeds. The graph in this slide shows the source of the colored bands on the airspeed indicator that will become very familiar to all pilots. The green arc on the airspeed indicator, known as the normal operating range, corresponds to the green portion of the graph. At these speeds, the aircraft, if it encounters a sudden increase in load factor from a wind gust or abrupt maneuver, will stall before structural failure occurs. However, in the yellow caution range, a sudden increase in wing loading could cause damage to the aircraft. This is why pilots should only fly at speeds within the yellow arc when the air is smooth. The red line on the airspeed indicator, the never exceed speed, corresponds to the red portion of the graph, where structural damage is likely to occur even in the absence of a gust or abrupt maneuver. Airspeed and angle of bank both affect the rate and radius of a turn. When airspeed is held constant, a larger angle of bank will result in a smaller turn radius and a greater turn rate. When angle of bank is held constant, a lower airspeed will result in a smaller turn radius and a greater turn rate. So, if a pilot needed to turn around in a valley or canyon, and was concerned about making the turn before hitting the other side, a lower airspeed and steeper angle of bank would improve the chances of completing the turn. A proper turn in an aircraft is made by coordinating the movements of the ailerons and the rudder. Although a turn could still be made with just one of these control surfaces, it would not be smooth and might even contribute to a stall. Thus, a right turn should be made by moving the yoke or stick to the right while simultaneously pushing the right rudder just enough to keep the black ball between the two black lines in the turn coordinator instrument. Too little right rudder will result in a slipping turn, and too much right rudder will result in a skidding turn. Sometimes, a pilot may want to deliberately use the yoke and rudder in an uncoordinated way in order to lose altitude quickly, such as in an approach to landing when the aircraft is too high. This maneuver, called a forward slip, is made by pushing the rudder far to the right while simultaneously turning the yoke in the other direction, balancing the two controls to keep the aircraft moving straight ahead even though the nose is turned to the right. The maneuver also works if these controls are reversed. Learning to use a forward slip to lose altitude will take some practice and should initially be done under the supervision of an instructor, since it is easy to stall the aircraft in this configuration if proper airspeed is not maintained. Another reason turns are made by coordinating both the ailerons and the rudder is to compensate for adverse yaw. This phenomenon, first noticed by the Wright brothers, is a result of differing amounts of lift on each side of the wing when a turn is made. The downward movement of the aileron on one side of the wing increases the camber, thereby increasing lift. Meanwhile, the upward movement of the other aileron spoils the lift, causing the wing to drop. However, the increased lift on the other wing also increases induced drag, which pulls the nose of the aircraft in that direction even though it is opposite the direction of the intended turn. Adverse yaw is corrected by pushing the rudder pedal in the same direction as the yoke and coordinating the turn. Torque is another aerodynamic force that can be attributed to Newton's third law of motion. For every action there is an equal and opposite reaction. The propeller, viewed from the pilot's seat, spins from left to right. This action causes a tendency for the entire aircraft to spin in the other direction, just like a hand drill when it is not held tightly. Torque is most noticeable at the high power settings during takeoff and is corrected by applying right rudder. Training aircraft do not have enough power to make torque a big factor, but high-powered fighter planes such as the P-51 Mustang could sometimes spin around upside down on takeoff. A modern modification of this aircraft for air races consisted of adding a counter-rotating propeller, which would counteract the effects of torque. The spinning propeller also creates another aerodynamic force called P-factor. The P just stands for propeller. At high power settings and high angles of attack, as in takeoff and climb, the descending blade, on the right, when viewed from the pilot's seat, has a higher angle of attack than the ascending blade, on the left. The right side of the propeller therefore creates more thrust. The aircraft will have a tendency to yaw to the left. This tendency can be corrected by applying continual pressure to the right rudder during the climb. The spiraling slipstream created by the propeller wash also tends to move around the fuselage of the aircraft and push against the vertical stabilizer, creating an additional force that causes the aircraft to yaw toward the left. Once again, this tendency can be corrected by applying right rudder pressure. Drag is another aerodynamic force that has powerful effects on an aircraft. There are two types of drag: induced drag and parasite drag. Induced drag is a byproduct of lift itself and its effects are most noticeable at lower airspeeds. As airspeed increases, induced drag decreases, but parasite drag increases. Induced drag occurs when the higher and lower pressure air meet at the wingtip. Remember Bernoulli's principle, creating a vortex. This vortex in turn causes drag. However, near the ground, the spiral airflow of the vortex is interrupted by the surface, diminishing the drag on the aircraft. This phenomenon is called ground effect. Because of ground effect, less thrust is required to overcome a reduced amount of drag. The aircraft may become airborne at a lower indicated airspeed than is necessary to stay aloft. However, ground effect becomes negligible once the aircraft attains a height of 1 wingspan from the surface. At that point, it must have enough airspeed to stay aloft or it will start to sink down toward the surface again. Pilots should compensate for ground effect on takeoff by pitching the nose of the aircraft slightly down after liftoff to accelerate to the best angle or best rate of climb speed. On landing, ground effect can cause the aircraft to float along the runway before touching down, especially if the approach is too fast. Pilots should compensate for ground effect on landing by maintaining a stabilized approach at the correct airspeed. The wingtip vortexes generated by induced drag are a hazard to any aircraft taking off or landing behind another aircraft that has just taken off or landed, especially larger ones. When landing behind another aircraft, make sure you touch down beyond its touchdown point. Wingtip vortexes are no longer generated once the aircraft stops flying. When taking off behind another aircraft, rotate prior to its rotation point. Wingtip vortexes aren't generated until the other aircraft starts flying. Also, maneuver upwind of the other aircraft to avoid the pathway of the vortexes blown by the wind. Aspect ratio is the ratio of a wing's span to its mean chord, the distance between the leading and trailing edges. A long, narrow wing has a high aspect ratio and a short, wide wing has a low aspect ratio. High aspect ratio wings produce less induced drag, so they are very efficient and produce a lot of lift. However, they are slow and less maneuverable. Lower aspect ratio wings can generate lift by moving faster through the air. In the 2 videos that follow, notice the different types of wings that have been utilized in these 2 modern manifestations of the ancient dream of flight. Afterwards, try to answer the sample FAA test questions on the remaining slides.
pounds for the